All right. Yeah. Welcome, everyone. So today we have Xavier Bouthillier. Sorry if I pronounce it wrong. Please correct me.
Good.
He's a sixth-year PhD student at the University of Montreal under supervision of Pascal Vincent. And he's specialized in machine learning and more specifically deep learning. And he's also known for his contributions in like tools such as Theano and PyLearn 2. And yeah, he's also like the lead developer of the project Orion, which is a platform for hyperparameter optimization. Okay, and then without further ado, yeah, Xavier, the floor is all yours.
Okay, can you confirm if you see the slides properly?
Yes.
Okay, I'll just reload to be sure for the animations. Okay, all right, so thanks everyone for attending. So benchmarks are very important in machine learning research. They are the basis of what provides us a metric to assess the progress of our machine learning research, or how new learning algorithms are better than previous one, and somehow they also are a substrate, let's say, for the new trends. As a very good example is AlexNet that was published on ImageNet that really convinced a huge amount of researchers that deep learning neural networks were a very promising area of research, despite what would say, let's say, statistical learning theory with respect to overparameterized models. And so benchmarks really is a very important aspect in machine learning research. But as with many, let's say, metric-based optimization procedures, there's often a risk of maybe optimizing the wrong metric or not optimizing it in the right way. So there's been many publications lately in a large area, wide area, so reinforcement learning, natural language processing, computer vision, recommendation systems, and so on and so forth, that have been raising concerns about the way we're benchmarking our algorithms. So the common concerns that we see across these papers is, well, first one is that there are often unidentified tricks that has a major impact on the results. So there's two issues behind this. First one is a question of transparency. So people are not necessarily identifying and sharing enough all of the bells and whistles in their work so that they can be reproduced. And another issue maybe is also that there's not enough ablation experiments that are conducted in the research papers to really try to identify in a given contribution what really is, what part of the contribution is really having a major impact on the results. Another common concern is with respect to hyperparameter optimization. And so in some of these papers, for instance, they have shown that if you give enough budget of hyperparameter optimization to the baseline, you could actually get results that are competitive with what was considered state of the art. And so there's a big concern in terms of, common ground comparison with respect to the hyperparameters for different algorithms. There's also a concern with respect to the robustness to variability. So it has been shown that if you train different models, so for the same learning algorithm, if you train it multiple times, you would have performance evaluation that are slightly different from one time to another. And so given two learning algorithms, A and B, it could be that you train once and you see that A is better than B, you train a second time and you see that B is now better than A. So the benchmarks, the way they are built, they are fairly sensitive to this variability. And finally, there's this question of generalization across tasks. So if I report results on a given task, on a given data set, let's say CFR10, and I show that my algorithm is better than another one, well, is it also true for a slightly different task, a slightly different benchmark of natural images, for instance? So this is another concern with how we're benchmarking learning algorithms. In this talk, I will focus mainly on the robustness to variability when we're benchmarking the learning algorithms, and also to some degree on hyperparameter optimization. We'll see how it's related to one another. All right, so when we are comparing learning algorithms, first I'd like to just distinguish clearly what is a learning algorithm and a model. So if we're thinking about deep learning learning algorithms, that would include, so the box here, learning algorithm, would include the architecture of the model. It would include the optimizer we're using, could also include like data augmentation procedures, whatever you including in the training pipeline, that's part of the learning algorithms. And so the model is just a product of this learning algorithm. And right, so when we're comparing learning algorithms or models, and in case of research, if we're doing research in machine learning, it's quite obvious that what we care about is the learning algorithm itself. It is not the model. Model is just an artifact coming from the learning algorithm. And the reason is that we're trying to improve the learning algorithm. And so when we're benchmarking some learning algorithms A and B, we want to compare not just the outcome models, but really the learning algorithm itself. I'll explain a bit more why later on. And this is also something that is true in the industry. So I've heard often people saying that, well, if the model is better for A and B, well, it is just better, and that's all we care about. We'll deploy this model, and that will be better. But even in industry, like they will be often sourcing new data, generating new data, also making slight changes in the learning algorithm. And as they're doing this, they are training new models, yes. But the next time they train a new model, that will not be based on the new model, that will be based on the learning algorithm itself. So they are building upon the learning algorithm, not upon the model. And so they should really make sure that the modifications they've made is improving the learning algorithm itself, not just a model. Okay, so that's the distinction between the learning algorithm and the model. And so in the benchmarking, let's say we're just comparing two learning algorithms to keep it simple, we'd have this this pipeline here. So we have the data that's coming to both. We feed them to some learning algorithms A and B. So we train a model. We have a different model for A and for B. And then we compare on some test data set, the performance of A and B. And we try to infer if the learning algorithm A was better than B based on the performance of the two different models. So then there comes this issue of variability. As we're training the models, they will be slightly different at every execution, because it will be impacted by for instance, the weights initialization, the ordering of the data during stochastic gradient descent, even the sampling of the data, or the way you're splitting train valid and test sets. There could be also source of noise in the architecture itself, such as dropout. And also, if you're using like a GPU, you would have numerical noise because of the random ordering of the operations that leads to slightly different results. And so when you are comparing the learning algorithms, what you care about is not just a single model, but the distribution of the models, right? So you would train multiple times the learning algorithms to have multiple models for A and B. And then based on these multiple models, you will compute the average performance of these different models, and you would compare the average performance of A and the average performance of B. You can also do a t-test accounting for the variance. I'll come back to that later. All right, so now we have, let's say, a setup where we can benchmark algorithms in a way that is robust to variability. But there's still an issue, which is respect to hyperparameters. So that this learning algorithm A here and B, they're not just fixed box, right? There are some hyperparameters that you can adjust, and it will impact the way they are performing. And obviously, when you're comparing some learning algorithms A and B, you want to compare them at their full potential. You don't care about some random parameterization. You want them to be to perform as good as they can. And so you want to fine-tune these hyperparameters. And in an ideal world, you would be able to fine-tune these hyperparameters perfectly with an infinite budget, but it's not the case. So you need to fine-tune them on a tight budget. And with this comes some considerations on how you could compare them properly. So let's say we have this baseline that was optimized in another paper, as it's currently done. Right? We just take the results from another paper and we compare it with ours. And so this baseline was trained with some hyperparameterization algorithm for some number of trials, and they picked this result here, the red dot at the end. So that's the best set of hyperparameters they found. And now we have our new learning algorithms, A, that we really love, and we want to optimize this as much as we can. So we do the hyperparameterization, and we run it for a huge amount of time with a large amount of trials, and we find better results than B. Obviously, that does not really make sense. I mean, it's not super reliable. Maybe you have a better result with A, but maybe if you've run with as many trials for B, you would have a good result, a similar results for B, or maybe an even better result. So obviously, you need to compare on common grounds. So similar budget for hyperparameter optimization with respect maybe to the complexity of the search space. So maybe they have different dimensions, different hyperparameters, different dimensionality of the search space. And you need to try to adjust so that they're compared on common grounds. But there's also another issue with the hyperparameterization, which is that there's also variability. So maybe once you've trained and you've run the hyperparameterization and you've had a regret curve like that, but maybe another time you would have one that looks like that, or maybe like that. And so then if you just run it once and compare A and B, it's not clear that the results you get is really reliable, saying that A is better than B. Right? There's some distribution also with respect to the different runs of hyperparameter optimization. And maybe B was better than A on average, but just by some luck, when you run it once, you had better results for A than for B. And so you also need to account for the variability at the level of the hyperparameter optimization. So going back to this scheme of the benchmarks for learning algorithms A and B, now we see that we need to integrate hyperparameterization in the pipeline here around A and around B. And we also need to do it in a way that we are accounting for the variance. So that would mean that we would run the hyperparameter optimization not just once, as we would typically do, but also multiple times. And so the different models here are the products of a different run of hyperparameter optimization. And obviously, most of the researchers now, they would just go bankrupt. They would not be able to run enough experiments to do this and have a reliable comparison of their learning algorithms. And so the main questions we wanted to answer in our work was, how can we account for these sources of variability without running hyperparameter optimization multiple times? And are these comparisons reliable if we do that? Right, so that was the questions that we've tried to ask with this paper called Accounting for Variance in Machine Learning Benchmarks that was presented in past March at MLSys. Right, so I already mentioned the questions. I'll just go quickly over it again. So what are the different sources of variance in the performance evaluation? And are every single one of them significant? And if it's not the case, maybe we can ignore some. And then what happens if we do? And ideally, we hope that the variance due to hyperparameterization is not significant, so that we ignore it. But we'll see that well, it's not really the case. Okay, so I'll go through 3 phases of experiments. This paper was very empirical, so going just through the different experiments will help understand main important observations and recommendations. So first phase of experiments, we tried to answer these 2 questions, which are, what are different sources of variance in the performance evaluation, and are every single source is significant? So I'll begin with weights initialization. Okay, we'll be training a VGG11 on CFAR10. And so we train 200 models, if I remember correctly, where the only thing is differing from one training to another is the weights initialization. So each block falling here represents the performance of a different VGG11, different weights initialization, where everything else is kept the same. So even that augmentation is seeded so that it's the same for each of them. So we have on the right the distribution of the on the left the distribution of the performances, on the right the standard deviation. Another source of variance is the data ordering. So we said before, so the ordering of the data during stochastic gradient descent. In this case, we're training again 200 models where we're only changing the ordering of the data during training, but everything else is kept the same. So in this case, for instance, weight initialization was the same for each of the training. And we can see the distribution of the performances affected by these changes. Another source of variability is the split. So typically we'd have fixed training, validation, test set, but especially in the case where the data is IID, this is just arbitrary, the split, so we could just randomly generate splits. In this case, we were using Auto Bootstrap. I can explain more in details during the question at the end if you want, but the main idea is that we're randomly generating splits, and you can see the variability here that is caused on the performances due to the random splits. And again, for each of the splits, everything else is kept the same. Then, as we just discussed, hyperparameter optimization is also, there's also some variability due to it. And so we were running a random search for a budget of, in this case it was 200 trials, 200 trials. And so we run just 20 random search in this case because it's super expensive. And in this case, everything is kept the same except the seed for the random search. So only the hyperparameters are slightly different from one execution to another. And we can see how it affects the distribution here. And finally, for a point of comparison, we randomized everything. So we ran 100 random search, where for each execution of the random search, we varied everything. So the seed of the weight initialization, data ordering, data splits, and the seed of the random search. But during a single random search, we are keeping the same seed, because otherwise we would be implicitly optimizing the seed as well. Right? And so we can see the resulting distribution of performances as we are randomizing everything. But this is just one task, and it would be a bit hazardous to try to draw a conclusion from this. So we run also on 4 other tasks. There's a segmentation task, a ResNet 18 on Pascal VOC. There is protein binding predictions, a simple MLP MHC dataset, and we had 2 birds, one trained on the glue SSD2 and one trained on the glue RTE. I'll get rid of the histograms because we really care about the standard deviation. And so there's 3 important observations based on these results here that I want to communicate. First one is the weight initialization, which is it's the gold standard in the literature. If we look at papers where they report variability of the trainings, typically they would vary the weight initialization, and that would be how they compute the variance of their training pipeline. And it's a bit concerning because we see that it's not the most important source of variability. There's just for the bird on the glue RTA, for which it was very important. And so that means that typically in the literature, we are underestimating the variance. And this is very bad because it means that we are overconfident in the conclusions that we're making. Another important observation is that the data splits is the most important source of variability. And it's not actually super surprising because it is the canonical source of variability in statistical learning theory. But as we're using fixed training, validation, and test set, we've kind of lost track of this important source of variability. And so also this result is concerning because, again, in the literature, we don't see so often random data splits or even cross-validation is not so often used now in deep learning. And so it's concerning to see that it's the most important source of variability. And finally, another important observation is that the random search in this case, and also for other sources of other algorithms that we've run, so that we had a random search, we also run for a noisy grid search. So it's a fixed grid search, right? There's no randomness in the grid search, but we randomly notch the search space. And there's Bayesian optimization as well as we've run with Bayesian optimization with MCMC, so that we're not so sensitive to the hyperparameters of the Bayesian optimization itself. We can see that for all of them, the variability due to hyperparameter optimization, and all of these were with a budget of 200 trials, is as important as weight initialization. And this is very concerning because, again, it is super expensive to run hyperparameter optimization multiple times, and so it's not affordable for most researchers. And so it means that we are kind of practically forced to ignore a source of variance that seems to be important. All right, so now second phase of experiments, questions we want to answer based on these results is, can we ignore some of these sources of variability? So we've seen that they were not all equally important. Maybe we can ignore some of them. So ideally, as we presented in the beginning, what we would do is we would run the hyperparameterization multiple times, right? So that's what we call the ideal estimator. So for k runs, we would seed everything. We execute hyperparameter optimization. We train and test with the best hyperparameters, and then we compute the average performance and the variance. So that means we would need to train T times K models, T here, being the budget for the hyperparameter optimization. An alternative is to just run hyperparameter optimization once and reuse the same hyperparameters for every trainings. So first we seed everything, we execute hyperparameter optimization, and then for each of the K trainings, we seed everything except hyperparameter optimization, and we train and test based on the same best hyperparameters we found at the beginning. And then we compute the average performance and the variance. So in this case, we would need T plus K trainings of models, so which is much smaller. So obviously, it makes a huge difference in terms of the number of trainings that we need to do as we increase the sample size, so the number of runs we're making. But the advantage with the ideal estimator, which is called the ideal estimator after all, is that as we increase K, so the number of trainings, its mean squared error will converge to 0. And this is mainly due to the fact that the variance of the estimator is function of the variance of a single run, sigma square here, divided by K, K here being the number of runs. And so as we increase K to infinity, the variance will decrease to 0. And since it is an unbiased estimator, will converge to the mean squared error of 0. But in the case of the fixed HPO estimator, we have that the variance of the estimator is bounded because it's the sum of correlated variables due to the fact that we're reusing the same hyperparameters. And so the correlation factor here, rho, will be bounding our variance. So even if we are increasing K up to the infinity, we will not converge to a variance of 0. But obviously, we're not running an infinity of seed, an infinity of execution, just a limited number of K. So we'll be looking at a simulation to see for a reasonable number of K, and also for correlation factors we see in our use case, how does it look like? So I'll be running simulations here. Each different whisker represents a different simulation. The bar in the center represent the average of our estimator, and the length of a whisker represent the standard deviation of our estimator. So each whisker is a different simulation, each of them with K equal 3. And at the top, we have a larger whisker, which represents the average and standard deviation of the estimator itself across the simulation. Okay. If we have a very good estimator, what we would have is that all the whiskers are aligned in the center, and the standard deviation of the big whisker at the top is close to 0. So as we increase K up to 100, we'll see that the whiskers are slowly aligning in the center, and the standard deviation is converging slowly to 0. And in this case, it's true both for the ideal and the fixed HPO estimator, because so far we've used a correlation factor of 0 for the fixed HPO estimator. But now if we increase this correlation factor, we'll see that the whiskers will slowly drift apart from one another. But this correlation factor that we are setting here is arbitrary, just 2. And so we'll look at the results we had from the first phase of experiments to see what this correlation factor and all looks like. So I'll be using the results of BERT on the glue RTE, but the results we have are fairly consistent across the different tests. First, we're running the ideal estimator. So we have a curve. The y-axis is the standard deviation of the estimator that is converging slowly to 0 as we increase the number of samples of the estimator. So remember, a sample here means running full hyperparameter optimization and reporting the test performance. So that means here 100 hyperparameter optimization. Now, if we do what is typically done in the literature, so randomizing only the weights initialization, we get, in this case, a correlation factor of about 1.05. And we can see that the standard deviation of the estimator is fairly strongly bounded by this correlation factor. And even if we go over, let's say, a value of K, 10 samples, we will not really improve the quality of our estimator. So just using the weights initialization is not giving us a very reliable estimator. If we randomize only the data splits, which was the most important source of variability taken alone, we see that the correlation factor drops to 0.3, and the curve here is going a bit more down. So maybe we can improve up to sample size about 20, but above that, we are strongly limited by this correlation factor. And finally, if we randomize everything except hyperparameterization, we have that the correlation factor drops to 0.08. And so we see that the curve is going much more down, but still we are far from the ideal estimator, and we could improve maybe up to 40 or 50 points. But above that, we're not gaining any improvement. And so the conclusion from this is that ignoring hyperparameterization or the variability due to hyperparameterization is harming the reliability of our estimation of learning algorithm performance. But at least if we randomize as many sources of variability as possible, except hyperparameterization, we can kind of attenuate this effect by at least decorrelating these model performance evaluation to some degree. So now the question is, okay, we see that it is harmful to ignore hyperparameterization, but maybe it is still possible to use this estimator to make a comparison in model and have a comparison that is fairly reliable. So we'll be running simulations with different comparison methods to see how reliable these comparisons are if we're using the ideal estimator or the fixed HPO estimator. So we'll be using two different comparison methods. First one is a typical one in the literature, so just computing an average. So giving a model A and a model B, we compute the average performance of A and B, and we compare them to some threshold delta, which is defined arbitrarily by the researcher, for instance, based on the literature. So it could be like the typical improvements that we've seen on the benchmark so far, or just what they consider to be a good improvement. So this is kind of very arbitrary. And otherwise, another comparison method we'll be using is the probability of outperforming. So it's a statistical test is based on a Mann-Whitney-U test. Again, given a model A and a model B, we train them, and for each pair of trainings, we compare whether A was better than B. And we do this multiple times. And at the end, say we have about 20 trainings, the proportion of the time that A was better than B is what we consider to be our measure of the probability of A being better than B. Now, based on that, we can compute confidence interval using a percentile bootstrap. If you're interested, I'll be giving a link at the end of the presentation where I explain in more details how you can compute this percentile bootstrap. And now, based on this confidence interval, we want to know two things. First is the result statistically significant? So this confidence interval here should be on the right of 0.5. If it overlaps or if it's on the left of it, it means that possibly B is actually better than A. And we also want the result to be statistically meaningful based on some gamma. So again, this is a threshold that is arbitrarily defined by the researchers based on some practical considerations. For instance, maybe deploying A would have some cost X, and so you want A to be better than B by at least some gamma to be worth the cost. And in this case, to be statistically meaningful, the confidence interval should overlap with gamma or B on the right of it. Sometimes we can have that the result is either statistically significant or statistically meaningful. We want to have both so that we can say that A is better than B. It needs to be both statistically significant and meaningful. Okay, just hide my video because I'm hiding the text. Okay. So we'll be doing a simulation with three different comparison methods: a single point comparison, an average, as I just explained, and the probability of outperforming. We'll be running simulations both on using an ideal estimator and a fixed HPO estimator. So we'll look more closely on this x-axis here to better understand what the simulation is about, how it's working. So given the model A and B, we are modeling the performances following a normal distribution based on our results in the first phase of experiment. So we have a measure of the average performance and the variability when we're randomizing everything. And so we can simulate based on that performances and our ideal estimator and fixed HPO estimator. So in the case of ideal estimator, we can sample from the normal distribution. So each row here of orange and blue strikes is a different simulation. And for a given row, we have different strikes representing different samples, so different sample of model performances that are a simulation. And we can also simulate the fixed HPO estimator by using our correlation factor that we've measured empirically, and by sampling skewed normal distribution based on this correlation factor. So as we move on this x-axis, as we're going to 0.4, we get that A is getting slightly worse than B, and as we get to the right of the x-axis, we have that A is much better than B, and we can see all the simulations are changing across this x-axis. And so given these simulations, we know for sure by construction that A is better than B by some percentage of the time, and so we can know whether the comparison method is wrong or not when it's making a prediction. So the y-axis here is the rate of detection, so it's how often a comparison method is saying that A is better than B. On the left, we have the null hypothesis, so A is not better than B. In the middle, from 0.5 to 0.75, we have that A is better than B, but not enough to be meaningful. So it's the gray region. And then on the right, we have the region where the the alternate hypothesis is true. So A is better than B by some significant margin. And so on the left, the lower the better. Since A is not better than B, we want our comparison method not to detect A better than B too often, right? It needs to be low. And on the right, the higher the better. A is better than B, so we want the comparison method to say that A is better than B very often. Ideally, if the data was actually normally distributed and we were running a t-test, what we would get as a rate of detection is this blue curve here. So what we hope for is that our comparison method using the ideal estimator and the fixed HPO estimator will have a curve that is as close as possible to this blue curve here. So first, the single point comparison, we drop the simulation to k equal 1. So we just sample one performance for each of the models and we compare the difference. We have a representation here of the different simulations. So the bar here must overlap with delta for the test to be positive, and then the square will become green, otherwise it will be red. So as we move to 0.5, where we have that A is actually equivalent to B, we have a rate of detection of about 9%, which is fairly high. We'd like to have not more than 5% here. We think of a level of significance of alpha of 5%, typical p-value of 0.05 we often hear about. And so 9% is fairly high. Now, if we move to 0.75, we get a rate of detection of 25%, which is very, very low. That means that we have false negatives of about 75%, which is very, very high. All right, so slowly it gets close to 100% to the end. So now we'll look at an average comparison with K, which is fairly high, right? 50. It's not necessarily something we often see in the literature, but it will make our results, our comparison more reliable. So again, we have these representation of the different simulations. The bar must overlap, must cross the delta here to be positive, otherwise it's negative. So squares are red when negative, green or positive. As we get to 0.5, the rate of detection is super low. It's close to 0%. So this is very good. But the counterpart of this is that as we get to 0.75%, the rate of detection is very low. It's about 6%. And so that means we have a rate of false negatives of about 94%. Often people would say that all we care about is really false positive, because we don't want to claim that some algorithm A is better than an algorithm B and just publish this paper when it's actually false. But we also care a lot about false negatives, because if you think of it, let's say some people run these experiments, and if they would run it an infinite amount of time, they would only find that A is better than B about 6% of the time, even though it is the case. And let's say someone ran it and gets that A is better than B, they published it, it's out, and now a lot of people try to reproduce these results using exactly the same experimental design. And let's say they shared all of the details of experiments so they can replicate it very reliably. And now you would have that about 94% of the people would find that A is not better than B. And typically what would happen is not that people will say, oh, this is because the design of the experiment, the way they're making the average comparison, this is why we have this high rate of false negative. No, what people would infer is that actually A is not better than B, and this was a false positive. Well, actually, the truth is that A is better than B. And so a really high rate of false negative is really misleading. And also, you would miss out on a lot of actual improvements you could make on your learning algorithms. So you really want to balance both the false positives and the false negative. It's not just the false positives that matters. And so slowly, as we get to probability of outperforming close to 1, we have the average that goes to a rate of detection of 100%. And we can see here the difference between the ideal estimator with the striped bar here, the dashed bar, and the fixed HPO estimator, which is the full bar here. By the way, the variability that we see here, the region here, is the variability across the different tests that we have. So remember, we had 5 different use cases, and so we run across all of them. So they have different average performance, they have different variability, and this gives us this variability here in the simulations. And so we can see the difference here between the ideal estimator and the fixed HPO estimator. And in either case, the average comparison is not doing fairly well. And the main reason is that it's difficult to set a good delta. And I have a bit of time, so I can go in more detail. So the delta here, that is arbitrary, as I said, the way we've set it in our simulations is that we looked on in the literature. So more specifically, most of these benchmarks that we're using were available on papers with code. And so we looked at the average improvements across the different publications across time on these different tasks. And we use this average difference as the delta that we're using here. And so it's slightly different for the different use case. And finally, we have the probability of outperforming. So here in this case, the visualization of the statistical test is this whisker that needs to be on the right of 0.5 to be statistically significant and must overlap with gamma or be on the right of it to be statistically meaningful. And so again, we want to be both statistically significant and meaningful, in which case the squares will turn from red to green. As we get to 0.5, we have a rate of detection using the fixed HPO estimator, which is very high, about 80%. So we can see that ignoring the hyperparameterization was quite harmful for the reliability of a comparison method using a statistical test. But in this case, the counterpart is that we have a better balance of false positives and false negatives. So as we get to 0.75%, we have a rate of detections of about 79%. So that means 21% of false negatives. So in comparison with the average performance, average comparison method, which was 94%, it is much better. And we can see in this case that using the ideal estimator, we have results that are very close to the ideal. So if we were in a situation where we can afford the ideal estimator, using a statistical test would be very good. So we get very close to the t-test. And then as we get close to 1, it converges to 100%. So the main difference here between statistical tests, such as the probability of outperforming and the average, is really that the threshold is, in the case of the statistical test, is a function of the level of variance. And so in a case where the variance is really large, you have that the threshold is increased. And in a case where the variance is very low, you have that the threshold is decreased. And so this is how you can have a better balance of false positives and false negatives, which is very difficult to achieve with an ad hoc average comparison, where you choose arbitrarily the delta. But it's also why the fixed HPO estimator was, let's say, degrading the quality of the reliability of the comparison method, because it's relying a lot on the variance estimation. And this variance estimation was not super reliable because we were ignoring the variance due to hyperparameter optimization. So I'll recap on the 3 different phases of experiments. First, when we discuss about variance, we've seen that the hyperparameter optimization, the variance due to hyperparameter optimization, is important. And we've seen that the data splits dominates, the variance due to data splits dominates all the other sources of variance. And the second phase of experiments, we've seen that the ideal estimator is too costly in general. We've seen that reusing the same hyperparameters and not accounting for the variance due to it is harming the reliability of our estimator. And we've seen that, well, at least we can randomize as many sources of variance to try to attenuate this effect. So we're reducing the correlation between our model performance evaluations. And finally, in the simulation phase, we've seen that the average comparison does not provide a good balance of false positives and false negatives because it's difficult to set arbitrarily the threshold. And that statistical test based on the fixed HPO estimator is maybe not as good as we would like. It's not close to the blue curve, but at least it's an appreciable improvement over a comparison method based on the average comparison. And so this gives us, let's say, an appreciable improvement that is reasonably good and cheap, but there's still room for improvement. So our recommendations based on that is that obviously we should execute hyperparameterization for all baseline. We've seen at the beginning it should be done on common ground so that this is not misleading. Also, if you're in a situation where you have, say, IID data and you can use random split, this is something we highly recommend because it's the most important source of variability. You should randomize as many sources of variations as possible because this decreases the correlation between the model performance evaluation. And finally, you should use a statistical test, just as the probability of outperforming, so that you are counting for the variance properly and have a result that is more reliable. So there are a lot of open questions following this work, but the two mains that I would like to convey with this talk here at the AutoML seminar is first, is there a way that we can estimate the variance due to hyperparameter optimization using surrogate models? There's been some NAS benchmarks in the past few years that are now using surrogate models. So instead of a tabular design of experiments, so that we can run the benchmark super fast. So it seems like it may be a promising area. The only issue we have here is that these surrogate models for the NAS benchmarks were trained with a very, very large amount of set of hyperparameters, or more precisely architectures and results. And in this case, if a researcher wants to evaluate the variance, it's not possible to run, let's say, 10,000 different set of hyperparameters to train the surrogate model. So basically what you would want to be able to do is to run hyperparameter once with a reasonable budget and use this data to fit a surrogate model that you could use to estimate the variance due to hyperparameter optimization. And so this may be a problem because with a very small amount of results, it's difficult to ensure that the surrogate model would be very reliable. And another important open questions, I think, is, well, we were talking about how we compare learning algorithms in general, like to make a publication, let's say, or to assess whether a new algorithm is better than another. But even during hyperparameter optimization, as we're running multiple trials, like let's say we have 200 trials, at the end of this run of hyperparameter optimization, most often you would have different set of hyperparameters that ends up with very, very similar performance measure. And now, given that there is a lot of variance in this evaluation of performance measure, how reliable is this comparison of different set of hyperparameters? And so when the HPO algorithm is deciding to go forward with some set of hyperparameters rather than other, how confident can we be that this choice of set of hyperparameters is a good one? And so there seems that there's somehow a trade-off between the number of trials that you can afford to do during hyperparameter optimization and the number of runs you should do to compute the average performance for a given set of hyperparameters. And I think this is something that should be investigated further to see how can we balance this trade-off so that we can do hyperparameter optimization in a way that is reliable. So that's it. Thank you for attending, and we have some room, I think, for questions now. About 10 minutes.
Yeah, thank you very much, Xavier. It was a really great talk.
Thank you.
And yes, so now there was a question on the chat from Matthias Zegger. I think it was on slide 36 or 37. And the question is, was this then average over several weight initializations?
Sorry, what is what?
Yeah, maybe Matthias can.
I think that's now, that's probably not